Welcome to Power Electronics Education Electronic Book, Lecture 3, Diode Rectifiers. This lecture is presented by Dr. FIRUZ ZARE. So let's find average output voltage for this full wave diode rectifier. We have found that this is line voltage. So if phase voltage is Vm sinus, for example 2 pi t over t for one of the phase, so line voltage, the peak value, maximum value, will be root of 3 times of Vm. So in this case, again, because we need to find output voltage, that means average over these intervals, for example this interval, so we can actually move the axis. That means we can actually consider this one, this voltage waveform, as a new voltage waveform. So we can define that one a cosine wave, root of 3 Vm cosine 2 pi t over t if we just move the time axis on this point. So then we just need to find this area and find this area based on simple method. So over one cycle we have 6 pulses, 1, 2, 3, 4, 5, 6, and then we can find pulse width. That means t over 6 is basically pulse width of each section. So if this is correct, then we can simplify the waveform. That means we can move the time axis on this point, and this is our voltage waveform over that cycle, and we just need to find this area, which is basically integral over this cycle. The lower limit of integration is minus t over 12, and the upper limit of integration is t over 12. So the output voltage is basically based on this equation. That means the average of the output voltage associated with one of the section over that time, which is t over 6. So basically we can simplify the equation. So that means root of 3 times of Vm is here. So then 1 over t over 6 can be simplified to this equation. So again, the integral of cosine 2 pi t over t is t over 2 pi sinus 2 pi t over t. The upper limit is t over 12. The lower limit is minus t over 12. So basically we can simplify again, because the upper limit means sinus 2 pi over t times of t over 12, and then that means sinus pi over 6. So same for lower limit, and then finally we get that voltage. That means sinus pi over 6 is 1 over 2, and sinus minus pi over 6 is minus 1 over 2, times of this minus is plus. So this is 1. So finally the output voltage is 3 root of 3 Vm over pi. Now let's analyze the effects of line impedance on output voltage. So in this case there is no line impedance. So what's happened in a simple diode rectifier when we have freewheeling diode? Suppose we have pure inductive load which can be defined as a current source. So for the first half a cycle, when we have positive voltage, this diode conducts, this diode is off, and then the current through the input is basically this current. And for the second half a cycle, basically because we have negative voltage, this diode is getting on and this diode is getting off. So let's consider on the transient. So what's happened just at this zero crossing point, and if we concentrate on this node, because the output current is constant, that means the sum of I in and IDM should be equal to I out. So what's happened when this diode is getting off? So in a very short time the current dropped to 0, and in a very short time the current through this diode jumped to that level. So in this case there is no element like inductor to control the IDT. So here we can see that there is a significant DIDT, and that's why we can't see any effect on line voltage. Let's look at this circuit diagram in which there is a line impedance, and now we are going to consider and analyze the effect of this line impedance on output voltage, input voltage, and also on the IDT. So here we can see that the current through the inductor is decreasing based on this DIDT, and also the current through the diode, freewheeling diode, is increasing based on this DIDT. So now we can analyze the circuit. So starting from this time, suppose this diode is turned on, so the current through this diode and inductor is output current. So this is current loop. So what's happened when the input voltage is getting negative? In this case this diode will be on as well. So there is a short circuit across the load. So over that time we can see that the output current is constant, but if we just concentrate on this node, this current, which is input current, plus current through this diode, should be equal to output current, which is constant. So that's why over this short time, when the input current is decreasing, the current through the freewheeling diode is increasing, and here we can see that the IDT has been affected by line impedance. So what's happened, basically we have short circuit when this phenomena happens. So in this case we can calculate the output voltage, because this phenomena happens two times, one here and the other at the beginning of positive cycle. So this one can affect output voltage, and also this one you can see that can affect line voltage. That means if this is grid voltage, because of this rectifier which has significant current, this voltage has been affected by this rectifier, and here we can see that this voltage is not pure sine wave. We can see that, for example, in the second half a cycle this diode is conducting. So when the input voltage is getting positive, that means at the beginning of first half a cycle, because the previous state, switching state, is this one, that means this diode is off and this diode is on. So just at the beginning of first half a cycle, what's happened? Basically we have positive voltage, that means this diode should be turned off, and we turn on this diode. And if we just concentrate on this node, because the output current is constant, so this current, which is line current, input current, plus current through this freewheeling diode should be equal to output current. So that means if we look at output voltage is 0 because there is a short circuit. There is a short circuit because when we have positive voltage, the current through the inductor is increasing, while current through this diode is decreasing. So that's why over this period it takes time to turn off this diode and to turn on this one completely. So that's why over this time there is a short circuit, the output voltage is 0, and also input voltage, that means this voltage, has been affected by line impedance. So we can find output voltage and commutation time, which is basically T1, when there is a line impedance. So what's happened? Basically when there is a short circuit, then we have commutation. That means the current through this diode or this diode is increased or decreased. But when there is a short circuit, basically the input voltage appears across the inductor, line inductor. So suppose that the voltage drop across these diodes are 0. So what happens in this case? The voltage across the inductor, which is basically this inductor, is L di dt, which is equal to input voltage. Suppose input voltage is Vm sinus 2 pi t over t. We can simplify this equation. So di, moving that one to the right hand side, so here we can get Vm over L sinus 2 pi t over t dt, then integral over that period. That means over this time current through the inductor is changing. That means current through the inductor is increasing. Suppose the output current is I. So that means the limits of integral, the lower limit is 0 and the upper limit is I. So for this function, the lower limit of integration is 0, the upper limit of integration is T1, which is basically this time. So in this case we can simplify. This is the answer of this integral, and we know that integral of sinus is minus cosine, so we can also put the limits of integral in this equation. So is minus cosinus 2 pi t1 over t minus times of minus, which is plus cosinus of 2 pi t times of 0, which is basically cosinus of 0, which is 1. So that's why this is the equation. So if we simplify that one and bring this term to the left side, so we have 2 pi Li over Vmt, and then we can rewrite that one into 1 minus cosinus 2 pi t1 over t. So basically cosinus 2 pi T1 over T equals to 1 minus 2 pi Li over VMT. So in this case, if we know all the parameters, then we can find this time. So T1 can be calculated based on this equation. Now let's calculate output voltage. Again, this is output voltage, so we can find based on this equation. So we need to find this area. So this is, we just need to find the integral over first half a cycle starting from T1 till T over 2. So again, the limits of integral is changed. The upper limit is T over 2 and the lower limit is T1. This integral is minus cosinus 2 pi T over T. If we put the limits of integral in this equation, for the upper limit we have cosinus 2 pi T times of upper limit, which is T over 2. This one equals to cosinus pi, which is basically this term, and when we consider lower limit we have this equation. So then cosinus pi is minus 1 times of minus is plus 1, so we can simplify that one. That means from the previous equation we found cosine 2 pi T1 over T as this term, and when we put in this equation we can get that voltage. The difference is that when we have no line impedance, the output voltage, the DC voltage, is Vm over pi, and when we have line impedance, this voltage is deducted from output voltage. So here we can see that if L is 0, then the output voltage is same as half wave rectifier without any line impedance. So here we can see that increasing line impedance not only change the power quality and affect the line voltage, but also change the output voltage. So using same method we can actually look at the effects of line impedance on output voltage in a single phase full wave diode rectifier. That means suppose these two diodes are conducting, and once the input voltage is getting positive, then we may turn on D1 and D4. But again, when we concentrate on this node, because the output current is constant, so the sum of this current plus this current equals to output current. So again, when this current is increasing, the other current is decreasing. So again, the input voltage appears across the inductor, line inductor, and then we have two short circuits. One is because of positive half a cycle, the other one because of negative half a cycle, and the output voltage can be affected by these short circuits, and then we can use the same analysis, same equation for this circuit. Now let's consider the effects of line impedance on output voltage in a three-phase full wave rectifier. Suppose these two diodes are turned on, D5 and D4, and now in phase A we can see that phase A is greater than, for example, phase C. So in this set of diodes we can see that D1 should be turned on, but because of line impedance, so the current through this inductor cannot be increased immediately. So that's why we need to actually look at the IDT. So if we just concentrate on this node, we can see that the output current is constant, is load current, and the current through the phase A plus current through phase C equals to output current. So in this case, when the input current is increasing through phase A, that means the current through D1 is increasing. The current through phase C is decreasing. That means current through this diode. But when we add together, sum of these current is equal to output current. So in this case again, we can consider the effect of line impedance by considering this short circuit. So this is the current loop. So basically this is the current loop that we need to consider, and based on that one we can analyze and find the output voltage and commutation time. Let's look at some examples. For example, in this case we have a diode rectifier with pure inductive load as a current source, and then we have different line impedance. So let's look at the voltage across this terminal. For example, for a short time there is a short circuit because of commutation. That means the current through the impedance, line impedance, is increasing, and the IDT is controlled by the line impedance. So that's why over this time here we can see that the input voltage of the rectifier is 0. So in this case, if we have a device connected to this terminal, so this terminal doesn't get a pure sine wave, or this terminal you can see that doesn't get pure sine wave. So that means if we have high power diode rectifier with inductive load, we may disturb the power system, we may actually change the power quality. So that's why we have to understand the concept of commutation, and also we have to control the output current, which means we can improve the input voltage and also voltage of the grid at different terminals. This is another example. Suppose we have high power rectifier with a large capacitor, and because the input current is not sine wave, the input current is basically has significant harmonics. So this current is not sine wave, so we have different voltage drop across these line impedance. So that's why the voltage at these terminals have been affected by this current. So this current or these currents are not sine wave. So that's why when we design a power converter, we should also consider the power quality. Especially for high power converter, we need to actually comply with IEC standard and also control the input current harmonics.